Today we are going to be solving polynomial equations, specifically solving polynomial equations of degrees higher than 2. So we're going to begin, however, reminding ourselves how to solve with a polynomial equation of degree 2, so quadratic polynomial equations. If we're asked to solve this equation, the very first thing I do is I think, can I factor it? So this one can be factored. I would factor this into x plus 4 and x minus 2. Be sure to FOIL back out, make sure that you did indeed factor correctly. And we find that x plus 4 must be 0 or x minus 2 must be 0 because we have 0 on this side. So x is equal to -4 or x is equal to 2. So two solutions to that quadratic equation. This one over here, finding the zeros. So if I'm asked to find the zeros, I take that function, set it equal to 0, and do the same thing I did over here, if possible. Can we factor that? Yeah, we can factor that. That factors into, let's see, we have a 1 and a 1. We're going to need the minus here and the plus here, and I FOIL that back out, make sure I can get that negative x inside. It all checks out. So now we have two factors multiplied together to equal 0, so one of them has to be 0. So x could be -1/3 from this factor, and x can be 1/2 from the other factor. So nothing new with those. If you can factor, factor. Same thing with degrees higher than 2. If you can factor, factor. If you cannot factor, that's when things get more interesting. If you cannot factor this, if we couldn't factor that, I would be using the quadratic formula or completing the square, one of the two. Alrighty, so what we got zeros here of -4 and 2. Look at our equation. Where might we observe these zeros to have come from? Well, these zeros are both factors of 8, right? 4 and 2 are both factors of 8. What about over here? 1/3 and 1/2, are those factors of 1? No, but 2 and 3 are factors of 6. 1 is the only factor of 1. So I'm asking you to observe those things because we're going to need to do that when we're solving polynomial equations of degree greater than 2. All right, so we are going to be, when we solve equations of degree greater than 2, like this one, we're going to be using a guess and check method. Okay, we're going to try to find one zero using guess and check. And when we use the guess and check method, we're going to be using that, what I just talked about up there. We're not going to guess just anything. If I was given this function, I would not guess, I wonder if 99 is a root. I'm not going to try 99 when I'm solving this, when I'm trying to find that 1 0. Once we find the 1 0, whatever it is, then we can rewrite this function as that x minus k times some quadratic equation, what we get when we divide that out. So, and then we know how to solve the quadratic equation, just like we did up here. Factoring or completing the square or quadratic formula. So what we're trying to do is get this down into a quadratic, and then we can take it from there. But we're using guess and check to get it down to a quadratic. So for this function, which number would you try first? We can pick any real number, but we can choose wisely and help ourselves. So just like we did up here, these were factors of 8. We're going to try factors of 6. Okay? And this is just walking through what we did up above. So to find the roots of f, I'm going to try factors of 6, which are plus and minus 1, 2, 3, and 6. Those are the factors of 6. And our zeros can be positive or negative, any of those factors. Okay, so I'm going to pick the easiest one, and that's a 1. So I'm going to try 1, and I'm trying it with synthetic division. So I'm trying 1 as a possible 0. I'm going to put the coefficients here. And now we're going to do synthetic division. So I bring down the 1, multiply, add, multiply, add, multiply, and add. And I do not get 0 for my remainder. Boo-hoo. We didn't get it on our first try. Okay? So if you get a non-zero number there, just try a different number. So go back to our list, scratch off positive 1. Let's try negative 1. Let's try negative 1 here. Okay, bring down our 1, multiply, add, multiply, add, multiply, and add, and yay, we got 0. We found one of our zeros. So we know that x equals negative 1 is 1 0 of, it's one root or 1 0 of the function. Okay, that means that x plus 1 is 1 factor of f. And it means more than that. It means that f of x is equal to x plus 1, that 1 factor, times what quadratic? Well, the quadratic that was left by this depressed set of coefficients. So x squared plus x minus 6. So we can rewrite f like that. Okay, we're still looking for the roots. We know one of them. How do we get the other ones? We take our depressed equation here and solve it for its zeros. So we're going to take x squared plus x minus 6 and find its zeros. It's quadratic, so I factor, quadratic formula, complete the square. If I can factor, I'm going to factor, and this can be factored. So 3 and 2 plus and minus will work there. So I got x is equal to negative 3 and 2. So what are the zeros of f? The zeros of f are negative 1, negative 3, and 2. Okay? All right, let's consider this polynomial function. What are its possible rational zeros? What would we try? Would we try 10? No, we wouldn't try 10. I'm looking at this number back here. Factors of this are 1 and 3, positive and negative. And then we also are dependent, our possible rational zeros also depend on 2, the lead coefficient. Its factors are just 1 and 2. So the possible rational zeros are factors of the last number, the constant, divided by factors of the lead coefficient. So plus and minus, factors of the constant, and factors of the lead coefficient. So this would be positive and negative, 1 over 1, which is 1, 1 over 2, which is 1/2, 3 over 1, which is 3, and 3 over 2, 3 halves. Positive and negative of each of those. So 8 possible rational zeros. But those are the only ones. So I would not try 2 or negative 2 or 4. These are the 4 that I would try. Okay? All right, and that leads us to a theorem. The rational zero test, also known as the possible rational root theorem. Some books call it that. Okay? If your function has integer coefficients, if your polynomial function has integer coefficients, they have to be integers, they cannot be fractions or anything else, then every rational zero has this form where p is a factor of the constant term, the very last term with no x, and q is a factor of the lead coefficient. Okay? Those are the only possible rational zeros. Okay? It tells us nothing about imaginary zeros. It tells us nothing about irrational zeros. Only the rational zeros. So let's find the zeros of this one. I think this is the one we were just talking about before. We already found the possible rational zeros. So the possible rational zeros that we're going to try are plus and minus 1, 1 half, 3, and 3 halves. And you can try those in any order you like. I like to try the easier ones first, so I will go and try 1 first. And if that doesn't work, I'd probably try the 3 first. If that doesn't work, I would go to the 1 half and the 3 halves. We will get very good at synthetic division in this section. Okay, make sure I copy these down right. All right. Bring down your 2, multiply and add, multiply and add, multiply and add, not 0, so I'm not even going to bother writing negative 12. I just know that this is not a 0. Okay, I'm now going to try negative 1. Okay, bring down the 2. Multiply, add, multiply, add, multiply, and add, and we do get 0. Yay! We found one, and it was cubic, so now I know I'm down to a quadratic, so I'm not going to have to guess and check anymore. I can rewrite g of x. Now I can rewrite g of x as x plus 1 times 2x squared minus 5x minus 3. Okay? Does this factor? Let's try it. Let's see, I would have a 2x and an x. I think it will factor. 3 and a 1 back there. 2 times 3 is 6. And if I subtract 1, I do get 5. I need this to be a negative and this to be a positive. And that's going to work. Great. So we're finding the zeros, so I'm setting this equal to 0. And so all of my zeros will be negative 1, negative 1 half, and 3. Notice that each of those was in that list. Okay? FYI, let's say that, and I'm done with this problem, but let's say that I had not tried 1 and negative 1. Let's say that I had tried that negative 1 half. Let's go and let me show you how that would work if you had tried negative 1 half. Okay, we would bring down the 2. Half of 2 is 1, so this will be a negative 1. Add half of 4 is 2, and it'll be a positive 2. Add Half of 6 is 3. This will be a positive 3. And sure enough, we confirm that that is a 0. Okay? All right. Number 6. Find all of the zeros of this one. It's a fourth degree. It's a fourth degree. So we could go through the possible rational zeros of this like we did this one. The possible rational zeros would be plus and minus 1, 2, and 4. I always like it when there's a 1 as my lead coefficient. Just like it makes factoring quadratics easier, it also makes finding zeros of higher ordered polynomials easier as well. So possible rational zeros are these. And I could go through the process for guess and check. However, I'm observing this and I can see that it is factorable. So if it's factorable, I'm definitely going to do that rather than guess and check. So how does this factor? Well, it factors with two sets of parentheses. We have x to the fourth, so I need x squared and x squared. And then I have a 4 back here. They're going to add to get a 5, so I'm going to need a 4 and a 1, both positive. If you FOIL this out, you will indeed get that. I'm going to set this equal to 0 because it says to find the zeros. Okay, so I have x squared plus 4 is 0, or x squared plus 1 is 0. Well, this gives me x squared is negative 4, and if I square root both sides, don't forget your plus or minus, square root both sides, you're going to get x is equal to plus and minus 2i, because you're square rooting a negative. A similar thing will happen here because we have a negative 1 on the other side. We're going to get x is equal to plus and minus I. So my zeros here are x is equal to plus and minus 2i and plus and minus I. There were no rational zeros for this function, and there were not even any real zeros for this function. So my question to you is, how many times does this touch the x-axis? None. There are no x-intercepts because every zero is imaginary. All right. So we know that imaginary zeros, complex zeros, come in conjugate pairs. Okay? The same thing happens with irrational zeros, irrational roots, square roots, things like that. Okay? And it makes sense if you consider quadratic functions and how those appear. How do irrational roots appear? Well, they appear when you square root both sides of something, right? So I have a little example here. If we're finding the zeros of this, I'm going to take that function, set it equal to 0 to find the zeros. Here I would get 9x squared is equal to 2, so x squared is 2 over 9. And to find x, we take the square root of both sides, plus and minus, and that would be square root of 2 over 3, conjugate pairs. Similar thing would happen if you needed to use the quadratic formula. Quadratic formula, it has that plus and minus in it. Those are conjugate pairs every time. Okay, so I'm telling you that p is a fourth degree polynomial function, and p has roots of square root of 5 and 7i. They ask us to write p of x in standard form. Well, if square root of 5 is a root, then negative square root of 5 must also be a root. If 7i is a root, then negative 7i must also be a root. So p of x must be x minus square root 5, x plus square root 5, x minus 7i, x plus 7i. That's the polynomial that has these roots. We want it in standard form, so we need to multiply this out. When I FOIL these out, I'm going to have x squared, the middle term zeroes out, minus 5. When I multiply this out, they're conjugates too, so x squared, the middle term zeroes out, minus 49i squared, so plus 49. And now we're going to FOIL again one more time, x to the 4th, plus 49x squared minus 5x squared, so plus 44x squared, minus 5 times 49, let's see, 45, 24, so 245. That's P of x. It has roots of square root of 5 and 7i. Okay, a couple more examples. Little review on this example too. Okay, this is the graph of f. Which of the following must be true? I'm always leery when I see the word must. Sometimes I've seen tricky multiple choice questions on the AP exam because of that word must. So that they don't use that nonchalantly. They're very deliberate with their wording on the AP exam. Okay, which must be true? F has, a little typo here, I'm going to need to get rid of that on your sheet. F has an absolute minimum value, but no absolute maximum value. Well, I see the absolute minimum value, and it's right here, whatever value that is. It exists. Does it have a maximum value? No, it does not, because those go to infinity. So there is no maximum value. So this must be true. Yes, I'm going to keep that one. Okay, what about this one? F is a 6th degree polynomial. Well, let's take a look. This 0, for degreed polynomials, one way to do that is to look at the zeros of the graph. This looks like it is likely a zero of multiplicity 1. Because it goes straight through, there's no little curve or anything. It looks like it's a 0 of multiplicity over 1. This looks like a 0 of multiplicity 3. It really does. Could be 5 though. There are no numbers on this graph. I have no idea what proportions it's in. I have no idea what these values are. This could be, 1,000, and this might only be 2, or this could be just 2, and that could be 1,000. We have no idea the scale here. So it looks like 3 vaguely, but I don't know. This looks like a multiplicity of 2, 0, but again, I have no idea the scale. Who knows? Plus, we really are not sure. I don't see any squiggles up here going on, but imaginary zeros can be hard to detect. So we're unsure of that. It does have to be even. The degree has to be even, but there is nothing to say that it has to be 6. So not necessarily. Likely, it looks like it, but it's not necessarily true. And that's where this must comes into play. Not necessarily. It could be true. It doesn't have to be true. Okay, how many points of inflection does this curve have? How many points of inflection? Points of inflection, remember, that's where concavity changes. So where a smile becomes a frown, that's a point of inflection. Or where a frown becomes a smile, that's a point of inflection. So right here we're concave up. Yeah, we're smiling. But somewhere it becomes concave down. It's a frown there, yeah? But then right here we starts smiling again. It becomes concave up there. But then somewhere here it becomes concave down. And then somewhere here it becomes concave up again. So I am seeing 1, 2, 3, 4 points of inflection, not 3. So the only one that's true is that first one. All right, a little bit of review with that one. Okay, oops, goodness. Okay, find all the zeros of this 5th degree polynomial. 5th degree. So we're going to find all 5 of them. What are the possibles? What should we try? Well, I was kind that I gave you a 1 here. I was not kind that I gave you a 5th degree, but I was kind that I gave you a 1 here. So the possible rational zeros are only dependent on this 27. So plus and minus 1, 3, 9, and 27. Only 8. Only 8 possibles. Not terrible. Okay, so let's try some. I always pick 1 to begin with because it's just the easiest to multiply. And so I'm going to write these out here in 1, negative 9, 28, negative 36, 27, and negative 27. Wow. Some big numbers. Let's see what we get. Okay. Bring down 1. Multiply and add. Multiply and add. Multiply and add. Multiply and add, multiply and add, and we're not going to get a 0 there. So we try another one. We'll try a negative 1. Bring down our 1, multiply and add, multiply and add, multiply and add, multiply and add. Wow. Are we going to get a 0 there? Absolutely not. No way. Try 3. Okay, bring down the 1, multiply, add, multiply, add, multiply and add, multiply, add, multiply and add. Yay. Okay, we found one. We found one. So that's good. So we know that 3 is a 0. The bad thing is that we still have a 4th degree polynomial. And we need to do something with that. So 4th degree, we have to keep doing our guess and check. Only I'm not going to guess and check using the coefficients that I started with. I'm going to guess and check using my depressed equation here, my depressed coefficients. So I'm using those. Should I try 1 and negative 1 again? If 1 and negative 1 did not work for these, is there any way it would work for this? No. So don't bother trying what you already tried and didn't work. However, could 3 be a double? Could 3 work again? It certainly could. So I'm definitely going to try it. It may or may not work, but I'm definitely going to try it. Bring down my 1, multiply, add, multiply and add, multiply and add, and it worked. It worked. Okay, now I'm down to a a cubic. I started with a quintic, 5 degree, and then I got down to a quartic, and now I'm down to a cubic. So I need to find one more zero. So far I know that 3 is a double zero. Okay, but now I have this depressed. I'm going to try 3 again. Before I try any of the other ones there. Okay, 1, 3, 0, 0, 1, 3. Sure enough, it worked. So, I forgot to put my little smiley face there. There we go. All right. Well, 3 was a triple zero. 3 was a triple zero. Would 3 be could 3 be another 0 here? No, it can't, because 3 is not a factor of 1. So absolutely not. 3 will not be any more. 3 was a factor of -3 though, or 3, yeah. 3 was a factor of 9, but 3 is not a factor of 1. So I don't have to bother trying it again. I do know though that p of x has 3 as a triple root, so I can rewrite that as x minus 3 cubed. And then my depressed quadratic will be x squared plus 0x plus 1. And if I'm looking for those zeros, I'm going to have x squared plus 1 is 0. So x would be plus and minus I. So the zeros of of p are 3 and plus and minus I, where 3 is a triple. Okay. All right. One last one here. Which of the following must be false? Which of the following is false? All right, let's go through these. This function has exactly one real zero. So they're telling me no imaginary zeros, only one real zero. Is that true or false? Well, I actually see that everything here has an x in it, so this is not going to be bad. I can factor out an x, and I'm left with x squared minus 2x plus 4. I get x is equal to 0 when I set this equal to 0. I get x is equal to 0 from that one. From this one, I can't factor it. This can't be factored, but I can complete the square, or I can use quadratic formula. Either one. I like them both. Since we only are interested in a real 0 or imaginary 0, though, I think I'm just going to use quadratic formula. So x is equal to 2 plus and minus. I'm really only interested in what's underneath this square root, because if that is negative, then we have imaginary zeros and only one real 0. If what's under the square root is positive, then we have 3 real zeros. So b squared is 4 minus 4 times a times c, and sure enough, I get a negative in here. So this is imaginary. So only one real 0, this is true. So that is not my answer, because we wanted to find the false ones. Okay, B. All cubic polynomials with integer coefficients have at least one real 0. If it's cubic with integer coefficients, it definitely has to have at least one real 0. Definitely does. So yes, that is true. And since irrational zeros come in conjugate pairs, and we also know that if it has integer coefficients, it has to have at least one rational 0. Right? Okay. So I circled that. I shouldn't have, because that is true. And I wanted it to be false. All right. Okay, this function they're telling me has 12 possible rational roots using the possible rational root test. Let's find out. I need factors of 6 divided by factors of 2. Factors of 6 are plus and minus 1, 2, 3, and 6. Factors of 2 are plus and minus 1 and 2. So that would give us 1 over 1, 1 over 2, 2 over 1, 2 over 2, but 2 over 2 is 1, and I'm not going to rewrite that. 3 over 1, 3 over 2, 6 over 1, 6 over 2 is 3, and we've already written 3, so I'm not going to rewrite that. Okay, how many are there? 1, 2, 3, 4, 5, 6, plus and minus, so 12. That is also true. So that means D has to be the false one. Why is it false? They're talking about x-intercepts. This h can be factored into x squared plus 8 and x squared minus 8. It's a difference of squares. And if we are finding the x-intercepts, we set that equal to 0. Do you get x-intercepts from that piece? No, you do not, because this thing is always positive. This is always positive, so no x-intercepts here. Do you get x-intercepts from that piece? Yes, you get 2 of them. Plus and minus square root of 8. Yes. So that function has only 2 x-intercepts, not 4. Okay, a variety of questions. Solving polynomial functions, I know that we could take our calculator and find at least we could have found the rational zeros to this. However, know that we are teaching you the concepts, we're teaching you the theory behind it. We're getting more than just the answer here. My concern is that you know the process and can learn to think critically and learn the process, practice the concepts, not just get the answers here. Getting the answer is fine, but there's more involved here than just get the answer.